way of doing science, particularly in the good sense, which is always interested on new things and opening venues for nice research. He has been focused in the last years very much on the nature of dark energy, and now in particular in the context of the DESI experiment. And a nice thing about the Berkeley lab, where he is, or he has been for 25 years or so, his staff, senior staff at the lab in the physics division, and you are at UC Berkeley as well as a professor. So a good thing is that he and other colleagues, theoreticians in particular, are involved in experiments since the very beginning or even before. And that's a nice culture when you go to places like Berkeley, that you see theoreticians sitting in the same room that engineers and experimentalists and phenomenologists, right? So I think it's very important to have them sitting in experiments. And he was from the very beginning of DESI, even before, probably with Boss. And he will tell us today about the dark energy. So please.
Okay, thank you very much. It's a pleasure to be here. Thank you for inviting me. So as Paco said, I'm going to talk about dark energy, and I'm going to, the talk will proceed from talking about some of the theoretical ideas that we have for dark energy and what it might be, and connect it to the observations, to the data that we have. So it was very exciting that earlier this year in April, the Dark Energy Spectroscopic Instrument, DESI, came out with its first year results. And instead of this point here, which would be the cosmological constant, its preferred region was somewhere off from that. And so that means that we have to really think very hard about what theory could explain that. And we need, of course, to keep moving forward with the data to explore it more. So I'm going to take you on a tour through that sort of thinking. The first thing before getting into specifics of the particular nature of our dark energy, what our universe has, is just how wonderful, how absurd, how exciting an idea cosmic acceleration actually is. We tend to forget about it. You know, yes, it was discovered more than 25 years ago. Yes, it won a Nobel Prize. And today we just accept it. But every day we should think of how amazing it really is. So in this classical picture of the expansion of the universe, we have a very rapid expansion in the early universe called inflation. Then we have a long period of where the universe is very dense with radiation, photons, and relativistic particles. And then we have a non-relativistic regime where there is matter and dark matter, ordinary matter plus dark matter. But then we have this sort of widening of this bell as the acceleration, the expansion accelerates as well. And so we hadn't really expected that there be any sort of turnaround like that. It's not part of, if you talk to a particle physicist, their theory of this. The standard model of particle physics does not include that. And so it was really quite a discovery 25 years ago. It's really affecting the universe on the very large scale. So it's quite amazing to think about how that is happening. We've learned since you were a toddler and you haven't learned how to walk very well, you fall down, you immediately know about gravity, okay? You may not know about the weak and the strong force when you're 2 years old, but you know about gravity, okay? And gravity is an attractive thing. You always fall down toward the earth. You don't suddenly, jump off the earth and go into orbit or something like that. So gravity is attractive. And so that should be slowing down the expansion. All of the matter and energy in the universe should be slowing it down, should be bringing it back together. Cosmic acceleration says, no, that's not what is dominating the universe. There is something that is speeding up the expansion. So something that is really working against gravity And again, every day you should think of how extraordinary that is. You shouldn't just say, "Oh, lambda CDM, oh, cosmological constant." Yeah, I've known about that since my school days. You should always say, "Wow, that is just something really extraordinary." Many people think so. So here's a selection back from shortly after the discovery, experimental discovery of cosmic acceleration by a few fairly well-known physicists, where they're really saying, hey, this is a big deal. This is a major problem, and we just can't call ourselves physicists who understand the universe until we resolve that. And 20 some years on, we don't have those answers yet. So one of the things that they talk about is it Einstein's cosmological constant? Which we don't understand either, but at least there are fewer questions about what you would need to do to understand it. The DESI data have shown that's not the preferred solution. And so there's many more questions that we can ask about what really causes cosmic acceleration. So as I said, on the data side, this is extraordinary. It really affects the universe in very, very fundamental ways. It's not like some particle physicist experiments where you are looking for, a part in 10 to the 10th effect in a branching ratio of some particles. This is governing the universe. This is the dominant effect. If we look at distances, so the expansion rate of the universe as a function of redshift or looking further back in the history of the universe, it's a huge effect. It's not a part in 10 to the 10th effect. It's an order 1 effect in that the expansion rate was slowing down, just as we said gravity should do. It's gravity being attractive. And now suddenly the expansion rate is increasing. It's accelerating. Okay? And again, it's not a subtle effect. It's a big effect. You can see it by eye on this sort of diagram. So on cosmic expansion, dark energy has a huge effect. The other thing that we're very good at doing is measuring the clustering of objects in the universe, how that grows. Again, gravity should be bringing clusters of galaxies together. It should be increasing the growth of structure, giving you more structure. And so in this plot, we're looking at the growth rate. So instead of how distances change, we're looking at how galaxy clustering changes. And the growth rate here is normalized to be 1 in the early universe, that it's behaving just like we expect under attractive gravity. And then here are 3 dark energy models. The black W of -1 is the cosmological constant. The other one is a little bit weaker than the cosmological constant. The other is a bit stronger than the cosmological constant. And again, we're seeing a huge effect, not a part in 10 to the 5, part in 10 to the 10, but order 1 or more effect, where that growth of structure shuts off. So here we are today, right here in the middle, basically. So this growth rate factor is measured to be just about a half today. But in the future, we see the prediction is it's going to shut off. Galaxy clustering is going to stop in the future. So again, the idea of dark energy, it's just completely governing our universe. It's an extraordinary question to ask, well, what is really giving us this physics? Because it's not in the standard model of physics. We have many, many ideas. We don't have any good ideas. Okay? So good, I've defined here as meaning that someone other than the authors of the paper believe in. Okay, that they would say, yes, that is the answer. They'd say, well, could be, but you're not going to get everyone to agree that yes, that is the answer. So the cosmological constant, written as lambda CDM, is the lambda cold dark matter theory. So if you go beyond lambda, which the data seem to indicate, then you have to have some extra dynamics in the theory. You can talk about that in terms of the pressure and the energy density. Often you take the ratio of those and you call it the equation of state W, so you'll see lots of W's through this paper. All you need to know is that W of -1 is the cosmological constant. If you're pulled off of W of -1 at all times, because cosmological constant is constant, it's always W of -1. If you're pulled off of that, you need another explanation. You need some sort of dynamical explanation. the simplest thing you can think of is I'm going to add a new ingredient, a new field. So you can think of it's like adding a new particle, but because we're on such large scales, it's not useful to think of it as a particle. It's more useful to think of it as just a sort of uniform field through the universe. A scalar field rolling in its potential. So there's some evolution that's going on, some dynamics. Or you could think of it as, well, gravity is not always attractive. I'm going to modify Einstein's equations, which are so beautiful, they work so well. Still, I'm going to modify them because maybe that's what the data is telling me that I need to think about. But it turns out that for most of the purposes of this talk, DESI, data, distances, and so forth, that is equivalent to just treating it as an effective field, even though there are other tests you can do to actually see the nature of the change in gravity. So let's now learn what can a scalar field do. So you're going to roll in a potential, you're rolling along. To some people, that's a horrible idea. There are people who gave talks at conferences earlier this year where they said, oh, this is so complex, we're going to call it this field a confusathon. They love lambda CDM. They love cosmological constant. They just want something flat, unchanging, no dynamics. That's all there is. And that if you allow something to evolve, then it's like going on a roller coaster. The field is just going all over the place. How are we ever going to figure out anything? Physics does not tell you that it can be this confusing. Physics actually tells you it's got to be very simple. And in the next several slides, I'll explain why. So that's why I titled the talk, Who is Afraid of Dark Energy? There are people out there who are afraid of anything other than a cosmological constant. And in fact, I'm going to try to convince you that the physics tells you there are only certain ways that the dark energy should act, and that we can understand the physics behind that. Okay, so the joke phrase that I like to use is dark energy does not exist in a vacuum. So it's a joke because cosmological constant is a vacuum energy. It's a ground state energy. But in fact, what we really mean is the dark energy is not alone. It has evolved in a universe that, as we saw, went through a long, long phase where radiation dominated, then matter dominated, and only today is it starting to accelerate. So you cannot just look at today. You cannot just look at dark energy alone. You have to take the whole sweep of the universe into account. And the fact that it evolved over many, many e-folds, many expansions, tell you how the physics, how the field is sort of guided into certain behaviors. In particular, there's a friction term, the same way as if you're on a roller coaster, there's going to be a friction. And that Hubble friction from this new radiation and matter evolution in the early universe will govern how the dark energy has to behave. So there's two basic possibilities. One, the friction can be very large, and then you're stuck on that roller coaster. It's not moving along the track because there's just too much friction. The field is frozen in place. Eventually, this Hubble friction, which again is due to the radiation and the matter density, the universe expands enough so that dilutes away, the friction goes away, and now you can roll. So we call that a field that thaws. Okay, it was frozen in place, and then gradually it can start to move. And so you have some classical potentials where you do that. The other possibility is that the slope, the steepness of the potential dominates over the friction. So if you're on a really steep part of the roller coaster, you're going to move even if there's a lot of friction. Okay, you are going to evolve and roll along. And here's some classical potentials that have that behavior. But eventually it can't be steep forever. It's got to get more shallow. And when it gets more shallow, then again, the friction comes in and the field stops rolling. And so we call that field a freezing field. So those are really the two possibilities that we have because you had this long period of evolution in a high friction era where there was lots of radiation, lots of matter. You can either move away from a cosmological constant, move away from an unmoving state, or you can move toward and unmoving state. As I mentioned before, there's going to be W's in this paper. So instead of dealing with the field and its derivative, we're going to talk about this phase space of this pressure to density ratio, W's. The reason it's convenient to deal with the equation of state is because the Hubble expansion rate, how fast the universe is expanding as a function of scale factor, is directly related to those W's, not as directly related to the field values. And in particular, if you're dealing with modified gravity, so what you have is not really a scalar field, then it's a little inconvenient talking about the scalar field value. It's more convenient to talk about these equation of state ratios.
Excuse me, can I ask a question about the equation that you just put?
Mm-hmm.
So those W's by do not depend on the value of the field itself or its derivative somehow?
It does. That's hidden in there.
Okay, sorry, I was confused because...
That's right. So you solve the field equations, which I'll show in the next couple slides, and then you derive what is the W as a function of scale factor.
Okay, thank you.
So here's exactly what you asked. I have different potentials. I can roll the field down them with different initial conditions. And I say, well, what does it look like in this W prime phase space? So again, you see there's these two broad regions that you get because you only have these two possibilities. Either friction dominates or the steepness of the potential dominates. These thawing and freezing classes. Let's make that a little bit better defined and ask, where would that field lie today? So today, we know is not just an arbitrary point in the history of the universe. Today, we know that we've got of the same order of matter density as dark energy density. So data tells us you've got about 0.3 of critical density in matter, about 0.7 in dark energy. Let's just say they're of about the same order. Okay, one isn't 100 times or 1,000,000 times more. And so you want to look at the endpoints then of these curves. And you see that they lie within one of these two triangular areas. The thawing area, where it moves away from a cosmological constant, no dynamics, W prime is 0, or toward a cosmological constant, this freezing region. And so we don't have a confusing roller coaster. We have fairly well understood physics from very, very simple principles that are going on. So that's an advance in understanding dark energy. It's very natural to then say, well, okay, that makes a lot of sense. What would happen if you lie outside those regions? So I've taken those two triangle regions here, and now I've talked about the regions around or in between them. We didn't used to do that. We used to say, no, we're going to just deal with those triangle regions because that's what the physics is pointing us to. But one of the very interesting things about the DESI results, they actually lie outside those two triangle regions that I said you should lie in. And so that says, well, all right, what would have to go wrong? What physical principle do you have to violate in order to be in each of these extra regions? So let's just very quickly go through that. So this high region here says somehow you did not evolve for many E-folds in a matter and radiation dominated era. And there's a couple ways you can think of doing that. But again, that's a very strange thing to think about because everything works so well. All the observations, agree so well with this early radiation and matter dominated era. I'm going to come back to that because the DESI data actually do lie up there by preference. There's this middle region where I said you had these two ideas. You had Hubble friction dominates, potential slope dominates. If the two balance each other, not just at one moment, but like almost all the time through the evolution, that's what you would need to be in the middle region. So it's not violating physics, but we call it fine-tuning. You're trying to balance these two very different things at almost all times. So we don't expect it. It's not physically impossible, but we don't expect it. And then this low region says that the field is not rolling down the potential, but it's rolling up the potential. There are ways to do that in particle physics, but it's not the first sort of thing that you would try, where we're used to things rolling downhill. And then there's this whole left half of the diagram where W is more negative than -1, the cosmological constant. This is called violating the null energy condition. And again, it's not something you expect at all. There are ways of doing it within physics, but it's very non-standard physics. So that gives you an idea of, even though we expect these two triangle regions to lie one way or another, we know what sort of physics we would have to change, what sort of standard assumptions we would have to violate to be in any of these other regions. Okay, a little bit of a actually comparing theory to data. It's really hard to take the data that we have, even excellent data like DESI and the CMB and the supernovae, and get two free functions of time out of it. It's a lot easier to fit individual parameters, individual numbers. So we'd like to be able to take these two functions and condense them down into two numbers. Nothing says you must be able to do that, but it's something we want to try to do. In particular, one thing that's hopeful is the observations we make, like distances, are integrals over these functions. And so you don't really care about the value at any one time, you care about its integral. And so the individual structure isn't as important as sort of the broad aspects. So maybe you could compress the information. And so let's take this diagram we showed before of these endpoints, these two triangular regions, and let's try to calibrate them, these two functions, into two numbers. Let's call W0 and WA. W0 is just, what is that value today, wherever the endpoints are? For WA, what we're going to do is we're going to take the time derivative and we're going to stretch the time axis in a very constant way, in a very particular way. If you do that stretching in a particular way, if you calibrate the relations, then you can see that these fans, where you have these broad regions, actually come down to these very narrow regions. There's also a minus sign, so this top part actually goes down to the bottom part, and the bottom part goes to the top part. But that's just because astrophysicists always like throwing in minus signs and logarithms to confuse people. So you can see that this fan up here becomes this really narrow little range over here. And this very broad fan becomes actually a few different families up in this upper region. And so if you use just two numbers instead of two free functions, yes, it's a compression, but it actually is a very accurate compression. And you can fit your data very well by doing this. And so that's what DESI went ahead and did. So now we're in the W0, WA regime. That narrow triangle that I showed in the previous graph from the thawing, which remember was the upper region when we were doing it in terms of the functions, WW prime, lies over here. Lambda CDM is where the dashed lines cross. And you can see that the preferred region is well off of both lambda CDM and the thawing region. The difference between the blue, the green, and the orange are slightly different data sets besides DESI. They all have DESI and CMB, and they use slightly different supernova data sets. There's really not that much importance in the difference between them. All of them lie off of both thawing and off of lambda CDM. So again, the answer that we're getting so far from year one of DESI, remember there's going to be 5 years of data, is in a very interesting place. So DESI calls it a tantalizing hint of a deviation from lambda CDM. You can see it's 2 to 3 sigma. So it's something that tantalizes you, but you want to do a lot more work. And of course, you want to understand it much better as well. So as I say, I'm not going to go into a lot of detail on what the statistical significance is. I'm not going to claim, yes, it's definitely not lambda CDM. And I'm not going to claim, oh, it's ignorable. I'm going to say, what happens if we take that best fit value at face value? What sort of physics do we need, since it lies outside the thawing region where we thought we should lie? And it turns out you need 4 different properties. You need to violate the null energy condition at z greater than 1. You need to then super evolve faster than the Hubble friction. So that's the part that looks like violating matter and radiation domination. You need to then, at later times, cross W of -1, what's called a phantom divide, and then evolve to less negative W naught. There are plenty of physics articles in the literature in the last 20 years of how to do each individual piece with various physics that, as I say, someone other than the authors may or may not believe in, but there are ideas out there. But all four together are very strange, is a very strange part of physics. But of course, theorists are clever and they'll manage to figure out how to do it. Before I get to that, the question of this crossing the phantom divide, crossing W of -1, is something that upsets a lot of people because a normal scalar field will never do that. You're always bounded on one side or another of it. You always need some extra physics added to it. And so people ask, well, is it just an illusion that you're crossing -1? Maybe, so let's, for example, look at this green and this orange curve. The orange curve never crosses W of -1. It's a thawing model which never crosses -1. The green does cross -1. If you compare them to data, they're both equally good fits. And so you could say, even though my fit looks like the green, the physics is actually the orange, where I'm not crossing -1. I don't have to go for crazy physics. And that makes a lot of people happy. The problem is, DESI does not point you toward that green-orange. DESI points you toward the blue. And so you can say, well, what is the best fit curve that I can get, which does not cross -1, this red curve, that gives you the equivalent parameters, but the true physics does not cross -1, compared to what we naively would say DESI tells us this blue curve. Can I trade the blue for the red curve and then not go for crazy physics? The answer is no. The red curve is 3 sigma away from the best fit value. So what looks like the data is telling us, if you assume the best fit is true, you really are crossing -1. So what we'd like to do is we'd like to test this framework. Again, we're testing the framework of the physics. Are we in some way violating this matter radiation domination? Are we crossing the phantom divide? And so forth. And this is very similar to what we do with inflation. There's simple theories of inflation. They predict the inflationary power spectrum tilt, the level of gravitational waves, and so forth. But then there's extensions that predict other effects like non-Gaussianity, whereas the simple theories say this should be very small. And so we're essentially looking for not quite non-Gaussianity in these theories, but non-standard physics. The equation of motion for the scalar field is called the Klein-Gordon equation. And so what we're really looking for is non-Klein-Gordonness. And you can get that in a few different ways. And what's going to turn out to be sort of, I won't say it's the correct theory, but it's a theory that has all 4 points that I mentioned before, is actually a late time phase transition, giving you the dark energy. You don't violate matter and radiation domination. It's just dark energy did not evolve from many E-folds doing it because it just came into being at a late time phase transition. That's one way we know how to agree with the data. Again, I'm not claiming that's the truth, but it's a lot more attractive to some people than saying we somehow violate radiation and matter domination, which works so well for so many different theories. DESI's released its distance data so far. We have many ways to test any theory we come up with beyond that. We also will have growth of structure data and make sure, are they consistent with what the expansion history, the distances are telling us? We can look for gravitational effects. Have we modified gravity? If we do, it will change gravitational lensing. It will change how gravity bends light. And then for gravitational waves, it will also change how gravitational waves propagate. So we will have, once we get the data for them, we will have many other ways of testing besides the DESI distance data. So now let me move from theory in the last couple of slides to talk about, well, where are we going to get this data from? Instead of the future looking bright, essentially the now looks really bright as far as getting data to understand dark energy even better. So I'm going to talk on the next few slides just about the results we're expecting to get within the next 1 year. We'll get new results in the distribution of galaxies, Lyman alpha 4s, quasars, large-scale structure in general, in the cosmic microwave background, and new supernova data. So let me run through each of these very quickly. The large-scale clustering data from DESI will be out next March, so not very long to wait. We'll measure the matter density power spectrum, so the growth rate, the growth factor, and the growth rate through what's called redshift space distortion. 3 years of distance data, baryon acoustic oscillation data from DESI will also be released in papers. So that's very exciting coming from DESI. Euclid is, of course, up and operating and going to have superb data on large-scale structure and on the gravitational lensing. Its release will also be next March, which will have about 50 square degrees. And so compared to DESI's 10,000 square degrees, it's much smaller area. It does go deeper, but still 50 versus 10,000. It's not going to overpower DESI. So this is just the start for Euclid. Euclid, of course, is beginning its own 6-year mission and will eventually get up to 15,000 square degrees. The cosmic microwave background, new analysis from the South Pole Telescope will come out very soon. I'm not a member of that collaboration, so I don't know exactly when, but I keep being told very soon by the people. And so that will be very interesting to see if that CMB data agrees with everything else that's out there. There is a new observatory called the Simons Observatory, which has a number of telescopes. So there are telescopes that started went on sky in April of this year, and you can see that they're adding more telescopes in 2026. Supernovae. There is a local supernova survey called the Zwicky Transient Facility. They've already released several papers discussing the properties of over 2,500 supernovae at redshift less than 0.2. They've not yet released the distances, the Hubble diagram. That to really understand all the uncertainties, that takes a long time. But they've talked a lot, they've had papers about the supernova properties. The Lacia-Schmidt-Sullivan survey will also get you lots of supernovae. That's on sky, very high cadence. Looking for lens supernova, which people here are very interested in as well and have their own projects for. So to summarize, we've got this amazing addition to the standard model, which affects the universe, distances expansion, affects the growth of structure. It really completely dominates the universe. And every day you should think, wow, this is quite a discovery. We do, however, understand the physics that factors into it. We understand what should work and what, if it doesn't work, what you need to change in the physics, what principle you need to violate in order for it to lie in a different part of the phase space. We were thrown a surprise. You know, the DESI data did not land on lambda CDM. They did not land in this preferred thawing region. They landed somewhere else. And so we're going to need to, tons of cross checks have already been done, but we're going to need to continue to do cross checks with more data, different types of data, large scale structure, CMB, supernova, and so forth. It's very exciting. So it's just like looking for non-Gaussianity in inflation. We're now looking for this non-standard evolution in how this dark energy behaves. And it may lead to something extraordinary. It is a phase transition. Phase transitions are always very fundamental physics where you're learning about some breaking of some symmetry. And so we might add a whole new sector to physics that way. And again, we don't have to wait, a decade for this. Within the next year, we're going to get so much new data that will be very high quality. It'll be very exciting to see what actually happens with it. So thank you very much, and happy to take questions.
Thank you very much for this exciting and bright future, especially for new generations. I think it's great. So any questions for Eric, please?
I wanted to ask you about tensions, the H-naught tension and the sigma tension. Do you think dynamical behavior of the cosmological constant can help alleviating them somehow, or what's your take on that?
Yes, so it's important whenever you're looking at one thing in cosmology, not to forget about everything else. The universe is very connected, so you don't want to focus only on H-naught and forget about large-scale structure or forget about dark energy. And you don't want to focus only on dark energy and forget about H-naught. So in the DESI paper, it goes through this. DESI actually finds consistency with Planck, the CMB experiments, on the value of H-naught. So it does not overlap with the Cepheid local distance ladder one. We know that the local distance ladder done through the tip of the red giant branch does get a value that basically overlaps with DESI. So this does not resolve that tension. Adding dark energy, even very strange phase transition like late time dark energy, generically will not work without throwing something else off. So we know that changing early dark energy alone does not work, as far as you might solve H-naught, but you'll make other things difficult. Changing late time dark energy, also you cannot get the whole network to agree well. Then sigma 8, because that's growth of structure clustering, then the DESI growth data will be very interesting for that. And as I say, that should come out in March. So I have nothing specific I can say about that at the moment. But you definitely want to keep an eye on this. I would not advocate to people doing their studies to do only the one thing. Do not put your whole career on H-naught, for example, because it can go away. So during my career, the H-naught tension has been 30 sigma at times. Okay, there used to be two groups, one getting around 50, one getting around 100. So it's not something that I worry about because I've seen it never. But I think, it will eventually work out.
But the sigma 8 is more interesting in that sense because it tells you about the clustering, and if you put some dynamical dark energy that tends to be like to be less contribute to in the opposite direction, like avoid clustering, that make it worse.
Right. So DESI has done the analysis based on its distances, CMB and so forth, the background cosmology that you get. What would that predict for sigma 8? And again, that does not, that agrees with Planck basically, but it has not used its own growth of structure data yet. That will come out in March.
Thank you.
Okay, thanks. Any more questions for Eric here or live? So what's the reaction of the particle physics community from their side? How they are reacting to this?
So one of the things I did not talk about that DESI does impact is neutrino mass. Yeah. So the particle physics community, I think, is more interested in what DESI predicts for neutrino mass, which is related to the sigma 8, because it's basically telling you how structure is, how clustering is suppressed or not. For the dark energy, the particle physics community, they're really not that afraid of phantom dark energy. I mean, people, they're very clever, very imaginative people, and they can come up with theories that do this. As I say, we didn't expect, no one really proposed a theory that had all four characteristics at once. But particle physicists like phase transitions. I mean, you know, lots of physicists like phase transitions. So it'll be interesting to see, do they pick up on that a little bit and come forward with theories for that? But there've been, there's been a lot of interest, but no one's put forward a theory that works perfectly for all of it so far.
And can you say something about the neutrinos constraint?
So to review what was out in the DESI papers, the neutrino mass constraint was very low. It actually preferred negative neutrino mass. DESI does not detect neutrinos in any direct way. It's again just looking at basically two aspects. One is the suppression of growth of structure. The other is really neutrinos have an energy density, and so they do affect the expansion rate. And so the negative neutrino mass really just means they prefer a slightly higher expansion rate, okay, which is very similar to what the W0 WA is saying. So when you hear about this neutrino mass, don't think that they're necessarily learning about quantum properties of neutrinos. But it's basically saying you want higher expansion rate. That would be a negative neutrino mass, which I don't think any particle physicist would be very happy with. But the uncertainties are broad enough that it does go into a reasonable positive regime as well. It's also very, very tricky because when you do an analysis, you always have put some priors. What range do you think is reasonable for the neutrino mass? And so the answer depends. Does it have to be greater than 0, the neutrino mass? Does it have to be greater than what the particle physicists say is the minimum of what they call the normal hierarchy? Or do you put some other physics prior in? The results change a little bit. So it's not disagreeing with the particle physics, but it's pointing toward something at the low ends.
Okay, thank you. Is there any questions or comments for Eric? Well, you can talk to him after the talk, of course. If not, René?
No.
Okay, well, we thank you again.
Thank you.
Thank you.